Okay, so hi everyone. So welcome back to this new video in this graph series. So today in this video we are going to do this problem from codeforces that was asked in round 457 div 2, and this problem is rated 2400, and this problem will utilize the concepts of lazy propagation on a segment tree and Euler tour, and along with it will also utilize the concept of binary lifting in order to find the LCA of two nodes in a tree, right? So that's why this is a very good problem, and it goes by the name Jamian tree. So I will provide a link of this problem in the description. You can check it out. So let us start with this problem now. So the problem reads like this, that Jami has given you a tree with n vertices numbered from 1 to n, and initially the root of the tree is the vertex with number 1. So the node 1 is the root of this tree initially, and also each vertex has a value on it. So each and every vertex present from 1 to n has a value associated with it, right? So everything is good till now. Then what happens is Jami also gives you three types of queries on this tree. So three different types of queries are given. So the first type of query is like this, that is 1 and then a integer v. So what does this mean? So let me zoom a bit. So it means that we have to change the tree's root, that is the current root, to a vertex with number v. So if initially the root of the tree is 1, then we have to change the root of the tree to this node, that is the v node. I hope this query is clear to you. Then another type of query is this, that is the second type of query, in which you will be given with three integers, that is u, v and x. For each vertex in the subtree of the smallest size that contains u and v both, we have to add x to its value. So it is simply saying that we have to find a subtree that contains this u as well as this v, and that subtree has to be of the smallest size, right? And in that subtree, for each and every node, we have to add this x to every node's current value, because initially every node has a value associated with it, if you remember. So this is the second type of query. And the third type of query is this, that is 3 space v. So we will just be given with one single integer v, that we have to go to this node v, and in the subtree of this node v, we have to find the sum of all the values associated with every vertices present in the subtree of this node v, right? So find sum of values of vertices in the subtree of vertex with number v. So these are the three types of queries that you will be given. And let's read further. So here the definition of subtree is given. So let us read it. So a subtree of a vertex v is a set of vertices such that v lies on a path from this vertex to the root of the tree. And pay attention that subtree of a vertex can change after changing the tree's root, right? So if the tree's root has changed with the first query, then by doing that the subtree of a node will also change. So I will tell you how this will be happening in the diagram. So what we have to do is show your strength in programming to Jami by performing the queries accurately. So in the input we will be given two integers initially, n and q, and the value of n and q can go up till 105 like this, and n means the total number of nodes present in the tree initially, and this q means the total number of queries. And after that we will be given with n different integers that can be from minus 128 to plus 128, and these n integers will represent the initial values associated with each and every node present in the tree. And after this we will also be given with a total of n minus 1 lines. So what this n minus 1 lines will do, so it will take the input of two integers, that is it will help to form the tree, right? And after that we will be given with q different lines, that is q different types of queries, which can either be of the first type or the second type or the third type, right? And all numbers in queries descriptions are integers, and the queries must be carried out in the given order. It is guaranteed that the tree is valid. So in the output for each query of the third type, that is this query, we have to output the required answer, right? And what is the required answer? That is the subtree sum for this node. And it is guaranteed that at least one query of the third type is given by Jami. That means at least we have to print one line of output. So this is the question, and here we are given with two different examples, right? And before moving ahead, if you are new to this channel and have not yet subscribed, please consider subscribing the channel, because as you can see that there are a lot of amazing videos already uploaded related to competitive programming topics, and if you want more such of these videos, then please subscribe and support. So let us move to the blackboard now. So as you can see that this is the very first example given in the problem, and in this problem here I have written the input, and this is the description of the tree that I have drawn here, and these are the queries. That is a total of 7 different queries, and the initial values are written on the top of these nodes, right? So the values written with red color denotes the initial values of the nodes. And if you remember, then initially we are also given in problem that this first node will be our root. So this is the root of the tree. So for now what I am telling you is, forget about the first type of query at all. So imagine like the first type of query never existed. So if you are never given with the first type of query and you are only given with the second and third type of queries, then what will happen? So suppose you are given a query here, something like, let's say the query is of the third type and the integer given is 3, like this. So if the query is like this, then it means that you have to calculate the subtree sum for the third node, right? So since our third node is present here, so we want to calculate its subtree sum. So the subtree sum will include the sum of each and every node values present in this tree, right? That is 2 plus 7 plus 8 plus 5. So you just have to print or return that value. So in this way you will answer this third type of query here. Similarly, if you are given with the third type of query something like 3, 1, then you will go to this first node which is present here, and then you will want to calculate its subtree sum. So we know that the subtree of this one is nothing but the complete tree. Why? Because this one is our root. So in that case you have to return the complete sum, that is 1 plus 4 plus 2 plus 7 plus 8 plus 5. So you just have to print or return this value. Actually you have to print this value, right? So in this way we will handle the third type of queries completely if you are not given with the first type of query. Similarly, if we are given with the second type of query, that is 3 integers u, v and x, right? So what we will do in this case? So let's consider an example of it. So for the second type of query, let us consider a real query. Let's say the value of u and v is 4 and 6 and the value that we want to add is 5. So if the query looks like this, right, then what we want to do, we want to find a subtree that will contain this 4 as well as this 6, and it has to be the smallest subtree, right? So as you can see here that this is the fourth node, this is the sixth node, right? So we want to find a subtree that contains this 4 as well as this 6, and it has to be the smallest. So if we go above this 6 till the root, and similarly if we go above from this 4 till the root, then the first node where it intersects is this third node. That is, this 3 will be the lowest common ancestor or LCA of this both 6 and 4, right? So this 3 will be the LCA of both 6 and 4. And the subtree of this 3, which will comprise of these 4 nodes here, will contain both this 6 as well as this 4, and it will be the smallest one, because this whole tree or the subtree of node 1 also contains this 4 and 6, but it is not the smallest. The smallest is this one, because it just consists of 4 nodes. And how we are determining this? We are determining this by calculating the LCA of this 4 and 6, which is this 3, and hence this subtree. So once we are able to find the subtree of this 4 and 6, we want to add a plus 5 value to each and every node. That is, we want to add a plus 5 value to this, to this, to this, and to this, right? So this is how we will deal with the second and third type of queries easily. And if any one of you is wondering that how we will actually calculate the subtree sum for a given node or update a range, then I think I have done these things in the previous videos as well. So let me tell you this quickly. So in order to find the subtree sum for a node efficiently, what we do is very simple. We first make a Euler tour of the given tree, right? And by making a Euler tour, we get an array. We get few things like we get the in time, we get the out time, we get the Euler tour array, ET array, right? And so we get something like this by doing the Euler tour. And after doing this, what we do is we pass this ET array into the segment tree, right? So in this segment tree initialization, we just pass this ET array. And after doing this, now if someone wants to calculate the subtree sum for a given node, let's say here we want to calculate the subtree sum of 3, then what we do, we just check the in time of this 3. So we will say the in time of this third node and the out time of this third node, right? So this will give us two integers, and these two integers will be nothing but the actual indexes present in this ET array, within which each and every node present in the subtree of this 3 will be present, right? And since this ET array will hold the actual value of the nodes, so that's why if now someone wants to find the subtree sum, we will simply use this segment tree and we will say t.query. We will just pass the range. So as I have said before, that is in time of 3 will be my leftmost index, and this out time of 3 will be my rightmost index. So in this way, we will be able to calculate the subtree sum for any node easily, right? And also now if someone wants to do a range update, that is if someone wants to update a subtree node's value by adding some new values, that is 2 plus x, 7 plus x, 8 plus x and 5 plus x. So if someone wants to do this, then again what we will do, we will simply calculate the in time and out time as we did before, right? In time and out time for this third node, and that will serve as the left and rightmost index present in this Euler tour array, within which each and every node of this subtree is present, and actually that node's value will be present in this ET array that we are passing here. And then we will simply say t.update the in time of 3 and the out time of 3, and we want to increase this by a certain value x, then we will simply say plus x. So in this way, this Euler tour along with this segment tree will help us in order to calculate the subtree sum as well as to update our subtree values. That is, either we can do plus x or minus x on each and every value present in the subtree of a given node. And since we are doing a range update and not point update, so that's why I can say this segment tree will be our lazy propagation segment tree. It will not be a standard one because we are not doing a point update here. We are doing a range update, and that's why this will be the lazy segment tree, and this will be our standard Euler tour, right? Nothing fancy. I hope everything is clear till now. But as I have told you that if this was the question, that is you just have to find the subtree sum for a given node using the third type of query, or to update the subtree's values, then this logic would be enough, right? That is, using this Euler tour along with this lazy propagation segment tree will always give us the correct answer in that case, right? But in this question there is a little twist, and the twist is that we are given with this first type of query, but since in this question you are also given with the first type of query, so that's why this is a good question. Because with the first query, what is happening is you are simply changing the root of the tree, right? Because initially the first node will be the root node, but it might be possible that as we will move forward with the queries, this 2 might become the root, this 3 might become the root, this 6 might become the root, or this 4 might become the root, or even this 5. So anything is possible now. And if the root of the tree changes, then the nodes that were present in the subtree of any node might also change or might not change. So what do I mean when I say this? So let's see with another diagram. So we know that this was the original tree given, right? And in this first node was our root node, which had a value of 1. Now what I'm saying is, let's try to change the root of the tree. So now if someone comes and tells you that the root of the tree is 3, so if the root of the tree becomes 3, then 3 will be our root, so it will be present at the top. So it will look something like this. That is, 3 will be now present at the top, and then these 3 different branches will float down like this. And if I write the values again, so this will be the new structure of the tree. And now we know very well that this 3 is the root, because I have told you to change the root of this tree from 1 to 3. So let me write that here. So what I have done is I have simply changed root from 1 to 3. So if I have asked you before to find the subtree of the node 3, then it will have comprised of these 4 nodes, that is 3, 6, 4 and 5. But now if someone asks you to find the subtree of node 3, so earlier it was this, but now it would not be this, it would be the whole tree. So the same thing I was telling you before. But if someone had asked you before to find the subtree of the node 4, then it will have only comprised of these 2 nodes. And now also if someone asks you to calculate the subtree of node 4, then it will again comprise of these 2 nodes only. So there are certain nodes in this tree for which the subtree has changed, and there are certain nodes for which the subtree has not changed. So if I mark it here, then the subtree of this 3 has changed for sure. For 4 and its descendants has not changed. Similarly for 6 it has not changed, but for 1 it has changed, because earlier for the subtree of 1 it consisted of the entire tree, but now it only consists of these 2 nodes. So it means that the subtree of this 1 has also changed now, and for this 2 it has not changed. That's why there are certain nodes for whose the subtree and the number of nodes present in it will change if we change the root of the tree. So this is a problem, because now if someone asks you to calculate the subtree sum of node 3, you will now want to calculate the subtree sum for this whole tree, but earlier it only comprised of this. So these two will give different values. By altering the root of the tree and changing the structure of the tree to something like this, it will also mean that you are simply doing what? You are simply changing the Euler-Tour values also. And if the Euler-Tour value will change, then the in time and the out time values that we have calculated before will also change, right? So those values will also change. And if you are not believing me, then let me quickly write the Euler-Tour, then you will realize how correct I am here. So if I try to write the Euler-Tour here, so since in the Euler-Tour array we push the values of the nodes and not the actual nodes, so that's why first it will be, so that's why we will travel something like first from this node to this node, then again to this node, then this node, then again here, then this, then this, then again something like this. So that's why the values that will be present in the Euler-Tour array originally will be something like 1, then 4, then 4, then 2, then 7, then 7, then 8, then 5, then 5, then 8, then 2, then 1. So this will be the actual Euler-Tour array. And now if you try to calculate the same thing for this second tree, then you will realize that our Euler-Tour has changed. Again we will start from this 3 because it is the root here, then we will go to this, then again backtrack, then 6, then again backtrack, then 4, then 5, then again backtrack. So in that case the values will be something like, first the value of third node, which is 2, then 1, then 4, then again 4, then 1, then 7, then again 7, then 8, then 5, then again 5, then 8, then again 2. So a total of 12 values should be present on both the sides. So if you calculate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and in this side also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And as you can see that these two Euler-Tour arrays are completely different now. Initially 1 was present before, now 2 is present. And the same thing will be true for the in time and out time as well. So if I write the in time and out time arrays here, so since a total of 6 nodes are present, so let me draw an array here quickly of the 6th size. So let us first try to fill it for the leftmost part, that is the initial tree. So we know that our timer always starts from 1. So in the very first second we will enter the first node, right? So let me zoom out this a bit. So in the very first second I will simply enter this first node, and after entering this first node I will be moving here. In the second I will be entering this second node, so that's why I will write 2 here. And then since I will move out of this 2 forever, that is I will not come back to it, so that's why in the out time for this 2 I have to write 3, and then again for 3 it will come like this. So for 3 it will be 4, for 6 it will be 5, for then here 6 it will be 6, then for 4 it will be 7, for 5 it will be 8, for 5 it will be 9, for 4 it will be 10, for 3 it would be 11, and for 1 it would be 12. So this is how the in time and out time arrays will look for the original given tree. And now if we try to calculate the same thing for this tree in which the root has been changed, we will enter this root right at the first second. So that's why I will write first on this third node in the in time array, then we will move to the first node here. So I will write 2, then I will write 3 for this second node like this, then I will write 4 because we are moving out, then again I will write 5 here because we are moving out, then we are entering 6, so we will write 6 here, then again we will move out, so I will write 7, then again I will enter 4 and then 5, so that's why it will be 8 and then 9, and then again I will move out, so it will be 10, and then again I will move out of 4, so it will be 11, and then finally move out of 3, so it will be 12. So now the in time and out time arrays will look like this. So as you can clearly see that the in time was before 1 2 4 7 8 5, but now it is 2 3 1 8 9 6, and also the out time before was 12 3 11 10 9 6, and now it is 5 4 12 11 10 7. So what I'm trying to say is very simple, that this Euler tool, this in time array and this out time array is completely different now. Why? Because we have changed the root, and now since we have changed the root, so now if someone asks you to find the subtree sum of this 3, then you cannot use these 3 data, you have to use this new data. But since we know that the number of queries can go up till quite high, I guess 1e5, and it will not be possible for us to always calculate these 3 values again and again, because this is a costly operation. So that's why what we want is that we just want to use the given initial data that we have calculated with the Euler tool, and just use this data in order to calculate the new subtree sum or to do the range update. We don't want to use this new value. So somehow we have to utilize the same tree without actually changing its root in order to find the new subtree sum for any given node, or to do the range update or the subtree values update for any subtree using the same tree without actually changing its root. So I hope you understood why actually changing the root and creating a new tree and then doing a new Euler tool will not be of much significance here. We want to utilize the original tree only in order to do everything. So now it is very clear to us that whatever query operations we will apply, we will only apply with the original given tree and not any other tree, even if the root is changing. Let us start performing these queries one by one, and if at any point the root changes, then I will tell you and make you understand how we will utilize this same tree in order to calculate the required values next time. Right? So let us start with the queries part. So initially the query is of the third type, and we want to calculate the subtree sum for this first node, right? So since this is the first node and the query is of the third type, so that's why we want to calculate the subtree sum. So this is the subtree of this first node, we know this, so it includes this whole tree, right? So that means we want to calculate the, so that means we want to add each and every value, that is 1 plus 4 plus 2 plus 7 plus 8 plus 5. So if I do this, then what it will be equal to? So 1 plus 4 it will be 5, 5 plus 2 it will be 7, 7 plus 7 it will be 14, 14 plus 8 it will be 22, and 22 plus 5 it will be 27. So that's why for the first query that is given here, the answer should be 27. And since the query is of the third type and we only want to print our answer for the third type of query, so that's why in the expected output, if you see, then the output should be 27. So here, as you can see, that in the output expected it is 27 here, right? So this is how 27 will come. And now if you move forward to the second type of query, then it is written 2463. So this 2 denotes that the query is of the second type, and then we are given 3 integers, that is 4, 6 and 3. So this 4 is our u, this 6 is our v, and this 3 is our x. So this is my u, this is my v, and this is my x here. That means we want to find a subtree that contains both 4 as well as 6. So since 4 is present here and 6 is present here, and this is the subtree that contains both of this 4 and 6, and it is of the smallest size which is possible. So that's why we will consider this subtree for this query, right? And in this second query, it is written that we have to add a +3 value to each and every node, right? So let's do it here. So we will say +3 here, +3 here, here and here. So the updated values will be something like this: 5, this will be 10, this will be 11, and this will be 8, and this will remain same as it is, that is 1, and this will also remain 4. So now this is the updated tree after performing the second query on this tree only, right? And since this is the query of the second type, so it means that we don't have to print anything. So in this way we are done with the second query, and now we want to move to the next query, that is the third query. So in the third query, it is of the third type, and the value of v given is 4. That is, we want to find the subtree sum for the fourth node. So since the fourth node is present here, and now we want to calculate the subtree sum, that is of this tree. So it will be simply 11 plus 8, right? Which will be nothing but 19, right? So if I write it here, then it will be nothing but 11 plus 8, that is 19. So this will be the answer for this query. And also if you see in the expected output, then after 27, 19 was written. So it means that we are going good till now. Now we will move forward, and now the query is the fourth one, and in the fourth query we are given as 1,6, that is the query is of the first type, and the value of v given is 6. So now things will get interesting, because now we have to change the root. So initially we know that this 1 is our root, right? But now this query is telling us to set this 6 which is present here as our new root. So if we set this 6 as our new root, let me draw this equivalent tree on this side, but we will simply be observing that tree and we will not be utilizing it, right? So keep this in mind. Now suppose you have changed the root, and since in this query we just have to change the root and don't print anything, so initially 1 was our root, now 6 is our root, which should actually look like this tree that I have drawn this side, right? So in this way our fourth query will be done, and what we have done is very simple. We simply updated the root value from 1 to 6 and nothing else at all. We just simply set our root value from 1 to 6 by using the equivalent operator. That's it. So now if we move forward, then this is our fifth query and it is of the second type, and again we are given with 3 different integers, that is 2, 4 and 5. So we are given with 2, 4 and -5. It means that we have to find a subtree now in which both 2 as well as 4 is present, and it has to be of the smallest size. So now since you know that the tree should be looking like this, and 2 is present here, 4 is present here, and the smallest subtree that contains both this 2 and 4 is this, right, which is rooted at 3. So in this subtree both 2 and 4 are present and it is of the smallest size. But if we try to look for the same thing in this tree for which we are actually operating, then 2 is present here and 4 is present here, and if we try to calculate the LCA, then this 1 will come out to be the LCA of this 2 and 4. And in that case, if we will add -5 value to each and every node present in the subtree, then actually it will add this -5 value to each and every node present in the subtree, But we know that this is not true because we only want to add -5 to these nodes and not this at all. So how we will make sure the same thing in this or this tree rather. So let me first apply the same thing of -5 to this side so that it will be easy for you to understand on this side. So it should be 5 minus 5, 1 minus 5, 4 minus 5, 11 minus 5 and 8 minus 5. So it will be 0, it will be -4, it will be -1, it will be 6, it will be 3. Okay, so it should look like this. So ultimately the tree structure should look like this after performing this fifth query, but I have not performed it yet on this tree, right? So how we will do this? Because in this tree it is easier for us to just get the LCA and add the values by doing the range update in the segment tree, but this thing is not possible anymore in this tree here using that standard concept, because now the LCA is changed, and if the LCA is changed then it will actually update the whole tree, which we do not want actually. So if you look carefully, then what is this 3 here actually? So this 3 here is the LCA of this 2 and 4, right? Somehow in this tree, if we are able to determine this third node somehow, that is the same node as the LCA of these two nodes in this tree, right? So if you are able to determine this node in this tree itself, then it will be very helpful for us, because since we just want to update this part and not this part, right? So what we will do simply is we will simply add this -5 value to each and every node present in this tree initially, right? So we will add this -5 value to each and every node, and after doing that it will also add this -5 value to this 6th node, which is wrong, and we do not want it to add it actually, because we know that 6 is present outside here and we don't want to add this -5 because it is actually not the present in the within the subtree of this 3, right? So 6 is not present within the subtree of this 3, so -5 should not be added to this 6. But I have told you that first add -5 to each and every value present in this tree. So if you will do this, then what will happen? So if I write here, then it will be 1 minus 5, 4 minus 5, 5 minus 5, 11 minus 5, 8 minus 5, 10 minus 5. So it will look something like this. And the values that are now present in the nodes for this tree are correct for each and every node except this 6. Because we know that the value that should be present at 6 after performing the fifth query should be equal to 10. But now it is equal to 10 minus 5, which is 5, which is wrong, which is not equal to 10. So now we want to determine a logic for which if there was any tree present in this part, that is this part, then we don't want to add this -5 to that value, to that region, or that to the subtree of this 6. So that's why if we are able to determine the same node as the LCA of this 2 and 4, which was 3 here in this tree, so if we are able to determine this 3, whatever nodes will be present in this region, right, whatever nodes will be present in this region, what we will do is we will simply again add a +5 to each and every node present in that tree, and by doing that it will actually cancel out the values that I have added initially, and it will ultimately remain equal to 10, which is same as of the correct rooted tree. So in order to understand this thing better, what you can do is, for a brief moment, consider that in this side there was another node present, that is the 7th node having a value, let's say 12, right? So it was present on this side, 7th node with a value of 12, and that's why, since I have told you that to add -5 to each and every node present in this tree, so that's why you must have added -5 to this also. That's why this would have turned to 7. But we know that anyhow the value of this 6 should remain to 10, and the value of this 7 should remain to 12, because it is present outside the subtree of this 3. That's why, since I have added a -5 to each and every node in this tree, now I want to make sure that except this region, that is this part, I want to again add the negative value of this x to each and every node, so that the values will cancel out and match the actual value that should be present. So that's why if we are able to determine this 3 in this tree, which is here, then what I will do is I will simply move one step down, which is this, and in that subtree I will again add the negative values. So if I do that, then I will add a +5 here, and again I will add a +5 here. So this will cancel out each other and it will again be equal to 10. Similarly, since I am adding a negative value of it, so 7 plus 5, which will be equal to 12 on. So again you can see that the values that are present in this tree are now actually the same values that are present in this tree, right? That is, for the 6th and 7th node it is 10 and 12, same here, which we wanted actually. So what we did was, instead of changing the root actually and treating the tree like this, we only worked with this tree. But what we did was, we simply added that x value to the entire tree first, and then we found a node, and for the subtree of that node we again subtracted or added the negative value of this x for that whole tree, and because of that the resulting tree is the same as the required tree. And since we have done this successfully, so let us move forward with the 6th query now. So now we are standing in the 6th query, and again see, it is telling us change the root to 4. So since now the root was 6 and now it is telling us to change the root to 4. So again, if the root changes to 4, then the tree will look something like. So now if the root of the tree changes from 6 to 4, so now the root is changing from this 6 to this 4. Then if I had to draw a separate tree, then it should look like this. So it should look like now this, that is 4 will be present at the top and the branches will hang down like this, right? So now this 4 is our root, but we know that we only have to deal with this tree whatever we want to do. We are just imagining it like this in order to understand better, right? So that's why here I will just change the root name. So in here it is 6. Now this 4 will become my new root. So let me write here, this will be my new root. So I am just changing the name from 6 to 4, nothing else at all. So that's why this 4 will be my new root. And let us move forward with the last query. So now we are at the 7th query, that is 3 3. So the query is of the third type and the value of v is 3. So we want to calculate the subtree sum for the third node. So since the third node is present here and we want to calculate the subtree sum, that is the sum of each and every value is present in this part. So it will be equal to what? It will be equal to 0 plus 10 plus 12 minus 4 minus 1. That is 22 minus 5, that is 17. So ultimately the required answer should be 17 for this last query, right? And we want to achieve the same thing in this tree now. So again I will do the same thing and I will apply the same logic that I have applied just before. So just apply the same logic, that is, instead of calculating it just for the third node, we will calculate it for the whole tree initially. So for the current state, if I tell you, then the whole sum will be equal to what? So the whole sum will be equal to, then it will be equal to 17 plus 6 plus 3. So it will be equal to 26. And please keep in mind that I have added this 7 for you in order to understand better. It is not actually present in the actual example. So the answer that will come after this query might not match. And since we just want the subtree sum for the third node, that is this part and not this part. So what we will do is, I will simply use this value minus this value in order to get this value, right? That is this 26 minus this 6 plus this 3, this 6 plus this 3, that is this, which will give me 17, right? So we just want to subtract the values of the 4th and 5th node. We will be calculating the total sum minus the subtree sum for this part, that is 26 minus this plus this, that is 6 plus 3. So that should give us 17 as the answer. So this is the overall logic that will be used in this problem, right? So let me tell you from the beginning what we did. So first we took the input of the graph, then I flattened this graph or tree into using Euler tool, right? And then I passed that Euler tool array into the segment tree. Why we did this? Because we wanted to find the range sum or range update. And also I told you that since the first type of query will change the root of the tree, and if we do this, then the Euler tool in time and out time, all of these datas will change. And again we have to pass this Euler tool to segment tree. and doing this repeatedly will be a costly operation. So it means that we can't do this and we only have to deal with the given original tree, and somehow we have to calculate the query answer every time. So here I told you that we wanted to update the values for this third subtree, right, which is actually this here in the original tree, but we cannot do it directly. So what I did was I added that required value to each and every subtree, and then I subtracted it from this part, and in that way the trees became equivalent. And the same thing we did for the query part also. That is, if we wanted to find the subtree sum for this third node, that is for this part, then what we will be doing is I simply calculated it for the whole tree and then I subtracted it for this part. The same thing I did here is I calculated it for the whole tree and then I simply subtracted it for this part in order to get the required query sum answer. So our main challenge is always to find this node for which we'll be subtracting our answer in the query part, that is the third type of query, and this node in the update part. And if you are able to do this, we will always be able to answer any query without actually changing the root of the tree. So what I tried to tell you was very simple, that if you are given a tree in which the initial root is 1 and in future the root is changed, so initially the root was 1 and then the root is changed, let's say the root was changed to 2. So if this is the case and then you are asked to calculate the subtree sum of 3, which will comprise of these nodes, right, so it will be the same answer that was present before changing the root. And why this happened? Because this 3 for which we are trying to calculate the subtree sum is actually not the ancestor of this root, but somehow instead of changing the root from 1 to 2, if I had changed it, let's say from 1 to 6, then in that case the answer would not have remained same. So earlier the answer was this part, but now since this is the root, so the tree should hang in such a way that the subtree for this 3 should now comprise of this part. So that's why if I write this logic here, that if the V is not the ancestor of current root, so if this V is not the ancestor of this current root, that is the root is present above this V, that is I'm talking about this case. So if the root was present here and this was our V, then in that case this V is not the ancestor of this root, right? So in that case our answer would have been calculated in the standard way by passing the in time and out time to the segment tree, that is either t.query in time and out time or t.update in time and out time by a particular value. So this would be our standard calculation. So things only got a little difficult when this V became an ancestor of this current root. So if this V is the ancestor of current root, that is root is present in the subtree of this V, that is I am talking about this case. So if this is the root, then this V becomes the ancestor of root, right? And if it becomes the ancestor, then the subtree of 3 will no longer remain same. So earlier the subtree of 3 was this, but now after changing the root, the subtree of 3 will become this, right? So doing it in standard way is not possible. So in order to achieve the same result, what we'll be doing is we will be first calculating the query sum, that is t.query, for the whole tree, right, for the whole part. And after calculating it for the whole part, I will be simply subtracting it for the query part of what? For the query part of the origin node that I have talked about. So I will calculate the total sum and then I will subtract this part in order to get the answer for this part. The same thing will be true if the root has been changed to 7 instead of 6. So if it has been changed to 7, so again what we would have done is we would have calculated the answer for the total tree, that is this, minus we would have subtracted it for this part. So this node here is the origin node that I am talking about, right? So this is the origin node, right? So if you are able to determine this origin node, then I can simply take the subtree part of that origin node through this and subtract from the total in order to get answer for the required part, right? And the same thing will be true for the update part also, that is I will first update the whole tree and then I will again apply the update operation, but for the origin node part only, that is the subtree of this origin node, but with a negative value of x that was originally given. So here I am applying this operation, update operation, to the whole tree with a given value of x, and here I am applying it to a negative value of x. So in that way I will get the tree that should look same when the root of the tree has been changed. So this is the concept. So in order to determine this origin node, since we already know the position, that is the number of current v and the number of current root, I will simply calculate the height from the initial root, that is 1. So the height of this v is 1 and the height of this root is 3. If you subtract this heights, that is 3 minus 1, which is 2, and again subtract 1, that is 1. What is this 1? So this is nothing but the kth parent of current root. So since our current root is this 7, so what will be its kth parent? That is first parent, so it will be this 6, and in this way we will be able to determine the origin node. We are able to do this because we know the position of this v and the root, right? So we will always know the position of the current root and this v if we are given with third type of query. But if we are given with second type of query, then for sure we will be knowing this position of current root, but we will not be knowing this v, that is the position of the node whose subtree is of the smallest size and contains both u and v. So suppose if the second type of query was something like, let's say 6, 4, 5, that is we want to find a subtree that contains both 6 as well as 4 and add a plus 5 value to it. Then if we try to do it in this tree only, then this 3 will be come out to be the LCA of this 6 and 4, and then we will be updating this plus 5 to this part. But we know that this is wrong because our root is this 7 now. But now we know the height of root, but we don't know the height of the part where these two nodes u and v will intersect correctly, because the root has been changed, so it is no longer 3. So if we try to imagine for the same tree that how it will look when this 7 is the root, then for that tree the LCA of this 6 and 4 will be nothing but this 6 only. Try to imagine that. So if this tree is inverted down, then 7 will become the root and it will be at the top, and the LCA of this 6 and 4 will be nothing but this 6 only. So that's why the origin node will be 6 in that case. And what is the height of this origin node? The height of this origin node is 2 and the height of root is 3. So here I will say 3 minus 2, that is 1, and then again subtract 1, then it will become 0. That is, we want to update the whole tree and then again apply a opposite update operation to the subtree of the kth parent of the current root, that is the 0th parent of the current root, which is this 7 itself, right? So in this part we want to apply the negative update operation, and if we do this, then it will give us the same answer as required. And how we will determine this origin node, I will tell you in the code part. We are able to again get the correct answer. So this will be the whole logic for this problem. I have told you each and everything in very detail, like how if the root will be present above the value of v, that is if v is not the ancestor of the current root, that is v is present below and root is present somewhere upwards, then we will do the standard operations, that is we don't have to worry about anything. But if root is being included in the subtree of the current node, then problem starts to appear. And in order to make sure we get the same tree as the changed root, what we did was we were simply applying the operation for the whole tree initially, and then we are simply applying it again for the part that we do not want. And in order to determine this second thing, we need this origin node. So in case of query operation, we are able to simply do this by subtracting the heights, right? It was not a big deal in case of query operation, that is the third type of query. But in second type of query, we are not given with v, rather than we are given with two values, that is u and v both, and using that two values we would apply some logic in order to determine this origin node. But anyways, if we are able to determine this origin node, then for the subtree of that origin node we will simply reverse the operation in order to get the correct value, and that will give us the correct tree with the correct values anytime. So this is the whole logic. So now I think it will be very good for us if we move to the coding part actually and code this up. So let us start writing the code now. So first we have to take the input of n and q, denoting the number of nodes and the number of queries. So after taking this input, we have to take the input for the initial values that will be present on the nodes, right? That is a total of n integers. And since I will be using 1 based indexing, so that's why I will be going from 1 till n, right? So this will be nothing but val of I. So that's why, since the total number of nodes that can be present is 1e5, so that's why I will declare a global constant here so that I don't have to write it again and again, right? And since I'm using 1 based indexing, so that's why a +1 extra. And then also declare this val array here, so it will be vector of int val, and the size of it will be this max n, and initially every value will be equal to 0, right? Or rather say initially every value will be equal to -1. So once this is done, we have to take the input for n-1 lines, because this will form the structure of the tree. So each line will consist of 2 integers, that is u and v. So take the input for both, and then since it will be a bi-directional one, so that's why I will say that g of u dot push back v, and then g of v dot push back u, right? So that's why let me declare this adjacency list globally here. So it will be vector int graph maxn, like this. So once this adjacency list has been made, so again we will move forward, and now we will start our Euler tour. And in order to start our Euler tour, we know that we have to store the values of nodes in an array. So we call it as Euler tour array, right? So declare it globally here only. So vector int Euler tour, like this. And since I'm using 1 based indexing, so that's why, to make sure that I never use the 0th index, I will push a dummy value in the 0th index. So I will push a -1 to that part, right? And then I will start my actual Euler DFS from the first node, and initially its parent will be -1. So now let us start writing our Euler DFS code here. So it will be of void type, and the name of this function is Euler DFS, and the first parameter is the node that I have passed, and the second parameter is its parent, like this. So this will be capital. So what we used to do in Euler tour, if you remember, so we used to maintain the in time arrays and out time arrays, right? So that's why we have to declare it here also. So I will say vector int in time array having the maxn size with initially each and every value equal to 0, and similarly the out time array with initially each and every value equal to 0, same as the in time array. So we used to maintain these two arrays, and also we used to start our timer from 1, right? Like this. So let us start writing it. So I will say that the in time for this node will be equal to this timer, and then I will increase the timer like this. So instead of doing it in separate lines, just do it here like this, right? And once the in time has been noted, I will push the current value of node, that is Euler2.pushback val of this current node, like this. And once this is done, I will explore the childs in the adjacency list for the current node, right? And if this child is not equal to this parent, so it means that I can go to that part and again call the same function like this. And this time our node will be this child, and the parent of this will be this node, like this. And once all the childs will be explored, I will now note down the out time array, because it is now time of backtracking. So out time of this node will be equal to this timer plus plus again, and finally I will store the value again in the Euler tool. So Euler2.pushback this val of node, like this. So in this way I have written the Euler DFS code here. So once this is written, next what I will do is I will declare a segment tree, and let's call this segment tree as T. And we know that what we have to do, we just have to pass this Euler tour array that we have just constructed into this segment tree, right? So let me paste my segment tree template here quickly. So this will be my segment tree template here, right? So this is a lazy propagation template that I have used, right? So I will recommend you to use your own template. So once I have passed this Euler tour array into the segment tree, it means that our tree has been successfully flattened and we can perform the query or update operations using this segment tree. And also, since we know that later we have the work of actually finding the LCA for two nodes, so that's why I will also use a tree template here. So instead of calling this segment tree as t, let's call it as seg tree, right? And this tree as t, so that it would be more meaningful to here. So here I have to pass two things, first the adjacency list and then the total number of nodes. So I will pass n+1 because I am using one based indexing. So let me also paste this tree template here, which will help us to calculate the LCA of two nodes. So let me paste it here. So this is my template here. So using this I will be able to calculate the LCA for n1 and n2. So once I have initialized these two data structures, we know that initially our root will be 1 as given in the question, right? So now what I will do is one by one I will explore the queries, right? So we know that first we have to decide what type of query we are given, that is the type of query. So we will take the input of type and we will see if this type of query is of one type. So if it is of the first type, then we will execute this block. Else if the type of query is of the second type, then we will execute this block. Otherwise, if it will be of the third type, which is the only remaining choice, then we will execute this block. And since for this third type of query we have to print an answer, so let's call it as result, and initially its value will be 0. And we know that the Euler tool that we have constructed here is such that the same value of node is pushed twice, that is once during the entry time and once during the output time, right? That is twice. So that's why whatever result will be there at the end, we will have to divide it by 2 because each node will be counted twice otherwise, right? So make sure that, and in between this will be our logic. Okay, let us start writing our queries types one by one. So if the query is of type 1, then we know that we will be given just one integer, right? So it will be called as v, right? So take its input, and what we have to do here, we have to change the current root to this v, right? So you have to change the current root to this v. So let's start doing it. So as I have told you in the explanation that in order to change the root, we will do nothing, but we will just, so I will just assign the value of this root variable equal to v now, that is root will be equal to v, and I will do nothing else. And the same thing I have told you in the explanation as well, right? So this, so in this way we are done with this part 1. Now if the query is of second type, then we will be given with 3 different integers, first u, then v, and then x. So take their input, and after taking the input, we know that what we have to do, we have to find a subtree containing both u and v such that this subtree is of the smallest size, right, and is of the smallest size, and add this x value to every node of that sub. So in order to do this, as I have told you that first we will find a origin node for this u and v, because it might be possible that the root of the tree has been changed till now, and since the root has been changed, so that's why the LCA of u and v that was useful before might not be useful anymore, right? So that's why you have to find the origin node. So I will call a origin function, let's call it as get origin, right? Get origin node. So this will be the name of the function here, and the value that it will return, let's call it as origin, right? So we'll call this function, and we have to pass this u and v both, right? So this function will give me the origin that I need. Let's write this function here. So int get origin node, int u, then int v, and inside this I will use this logic. That is, first I will find the LCA between u and v, then I will find the LCA again but between u and root, and then again I will find the LCA between v and root, right? and then I will say that best node will be my this A, but if the depth of this B is actually greater than the depth of this A, or let's say best, then our best will change and it will become equal to B. Similarly, if the depth of tree, that is depth of this, this will be greater. So if depth of this C will be greater than the depth of this current best, then again our best would change and it will become equal to C. And at last we just have to return this best. So let me pass the root here. So pass this root here, right, as the third parameter. So this will be the root, and this best will be our actual origin node that we need. And I think I also need to pass the tree here. So let's pass it like this. So also pass the tree here as the fourth parameter like this. So once the get origin function is written, so it will give us the origin node. And now what we will do, so I will just check if this origin node that I have got is the same as root or not. So if it is the same as root, it means that I have to update the whole tree, right? So it means that I have to update the whole tree, and in order to update the whole tree, I will simply say segment tree dot update the first starting index, that is 1, till the total size of the Euler tour array. So let's say it as Euler tour dot size -1 like this. And we also have to pass a third parameter, which will be the value that we want to increase with, so x. So in this way I will write this if call. Else if, now if this origin that we have got is not equal to root, so if it is not equal to root, then it means that either this origin can be present below the root or above the root. That is, this origin can either be the ancestor of root or not the ancestor, right? So if this is not the ancestor, that is, this origin is not the ancestor of this root, that is, root is not present in the subtree of this origin, so it means that root is present somewhere above and origin is present below. So there is no problem in updating the subtree of origin at all, right? So I will simply write here segment tree dot update the in time of this origin till the out time of this origin with a value of x like this, right? So let me write this ancestor function also here. So this will give a boolean value, and I have passed two things here. First the origin node, and second the root. So how we will determine if this is the ancestor of this or not? So for this we will just utilize the in time and out time arrays. So this is very simple. We will simply check if the in time of this origin is less than or equal to in time of this root, first condition, and if the out time of this origin is actually greater than or equal to the out time of this root, right? So if both of these conditions are true, it means that this origin is an ancestor of root, otherwise it's not. So the same thing it will pass here, and if it is true, then this block will be executed. And if this is not the case even, then it means that the root is present in the subtree of origin, right? So that's why we cannot update the whole subtree of this origin directly like this. So we will apply the technique that we have discussed. That is, first we will update the whole tree. So I will say segment tree dot update from first till last index like this with a value of x, and then I will again update it in future, but only for the origin part, that is the in time of root's kth parent till the out time of root's kth parent, right, with a value of this x. So I will do this in future. So once we have updated the complete tree, now we know that what we used to do. We used to calculate the height difference. So we used to calculate the height difference, right? So I will just say height difference will be equal to t dot depth of this root, because we know that root is present in the subtree of origin. That is, the height of root is more. So that's why we are writing it first, minus t dot depth of the origin like this. So here we have already calculated the origin, right? So we will take the height difference of both, and whatever height difference will come, we will again calculate a value which will be the root's kth parent like this. So root's kth parent will be equal to t dot kth parent, and we want to check the kth parent of the root by a distance of this height difference -1, as I have told you in the explanation. This, right? So first we are updating the whole tree, then we are calculating the height difference, then whatever the height difference is, we are just taking one less than it and actually calculating the kth parent of the current root, right? So that will give me the correct origin node. So, and in this way I think I have written the type 2 query completely. Now let us move to the third type of query, and as I have told you that most of the things will remain same here. That is first we have to take the input of an integer v like this, and then we will simply check if this v is the same as root. So if it is the same as the root, then it means that we have to return the complete sum of the tree, right? So I will just say or set my answer as segment tree dot query starting to ending, that is this, like this, right? But if it is not the case, that is v is not the same as root, so this will be nothing but the result and not answer. So if this is not the case, that is v is not the root, so either root can be present above this v or below this v. So if it is present above this v, that is v is not an ancestor of this root. So if this v is not an ancestor of this root, then it means that we have to set our result simply like this. That is, we don't have to subtract anything, we just have to find the subtree sum for this v without any problem, because it does not contain the root as of now. I will write segment tree dot query from the in time of this v till the out time of this v, like this. But even if this is not the case, then it means that, so let me give comment to this condition also. So this is the condition of returning complete sum of the tree, right? And this is the condition of when root lies outside the required subtree. So there is no problem in calculating the subtree sum at all. But if this is not the case, then it means that the root is present within the required subtree, right? So here I will first calculate the answer for the whole tree, as I have told you in the explanation. That is this, like this, starting from 1 and going till all the way till the last index of the Euler 2 array, like this. So first so it will be result. So once I have calculated the answer for the entire tree, that is the total sum, now I have to subtract the sum, right? So again I will calculate the height difference, that is I will say t dot depth for this root because it is present below, minus t dot depth this v that is given in the input. So this will be the height difference, and then I will say root's kth parent again. So I will use the same variable naming as here, that is root's kth parent. So it will be t dot kth parent. I want to find the kth parent for the current root by a distance of this height difference -1, and I will simply subtract the current answer, that is the total sum, to this, that is segment tree, that is seg tree dot query the in time for this root's kth parent till the out time for this root's kth parent, like this. And at last whatever answer will be there, that is result, I'll simply divide it by 2, and at last just return. Since this kth parent value can be negative, that is -1, so if you look in the tree template, then this kth parent can also return a -1 value, right? So to make sure that that is not the case here and our code runs fine, what I will say is I will only run this statement if this root's kth parent is not equal to -1. So if this is not equal to -1, then only I will execute this query, that is update. The same thing I will do here also. So if it is not equal to -1, then only I will run this query. So now I think I have written the complete code here. So let us run the code and see if it is working fine or not. I think I have found the bug here. So as I told you that when the query will be of the type 2, and if this is the case, then it means that I have to apply the operation twice, first here for the whole tree and then here for the subtree of the origin node, that is the root's kth parent. And while applying the operation second time, I have to actually pass the negative value here so that only the operation will be reversed. So now I think it is correct, and now if I run, let's see. So as you can see that both the test cases are getting passed completely here. So let us try to submit the same on the platform and see if we are correct or not. So as you can see that our solution is accepted finally, and this is the code that we just wrote, and I have explained you each and everything in very detail, what is the logic behind all this. So thank you so much for watching this video till this point. If you really think you understood something new and which can be helpful in your upcoming interviews, please consider subscribing the channel, because it takes me a lot of efforts to create these kind of videos, right? So yeah, thank you so much for watching this video. Thank you.